All right, guys, in this lesson, we're going to review probability, or as much as we can get to. So, right off the bat, when we're looking at probability, we have this idea of a law of large numbers. And so, when we think about probability, we think about relative frequency, and that's the proportion of times that an event will happen, or basically the number of successes divided by the total number of trials. Or that's how we find relative frequency when we're talking about probability. However, there's this idea of a law of large numbers when we're thinking about probability, and that's when an experiment is repeated a large number of times, the relative frequency of an event comes closer to the likelihood that it will occur. And so really what we're trying to get at here is that probability is empirical, it's not theoretical. So the probability, the long-term relative, is basically the long-term relative frequency of an event. If we took so many trials of this, if I flipped a coin 100 times versus 1,000 times, the odds of me getting heads 50% of the time is going to be closer when I flipped it 1,000 times than it is when I flipped it 100 times. That's kind of the idea behind the law of large numbers. So hopefully that makes some sense. So when we're looking at this, let's look at an example. There are two games involving flipping a fair coin. In the first game, you win a prize if you can throw between 45 and 55% heads. In the second game, if you win if you can throw more than 60% heads. And so for each game, would you rather flip 20 times or 200 times? Well, I know that if I'm trying to get closer to 50% heads, then I want to make sure that I flip it as many times as I possibly can. So for the first game, you would want a large number of trials, so you would probably take 200 because the probability of heads on a fair coin is 50%, and so I want to make sure that I land somewhere in between 45 and 55, so I want to make sure that I flip that multiple times. Whereas in the second game, since 60% is further away from 50%, or from that expected value, you might get a wide swing in relative frequency on a smaller number of trials, so you would want to do 20 flips. Remember, there is no law of small numbers in this case, only a law of large numbers. So hopefully that kind of brings a little context to this. Let's look at another example here. And this one's going to kind of define how we look at just basic probability from every angle. So a standard literacy test consists of 100 multiple choice questions, each with 5 possible answers. There is no penalty for guessing. A score of 60 is considered passing, and a score of 80 is considered superior. When an answer is completely unknown, test takers employ one of the 3 strategies: guess, choose answer C, or choose the longest answer. The table below summarizes the results of 1,000 test takers. So basically what they did was they took 1,000 test takers right here, and they made them choose whether or not they were going to guess on every question, just choose answer C on every question, or choose the longest answer on every question. And then what they did was they tallied up their score based off of how they did. And so, we had 40 of the 300 who just chose to guess on every single answer. 40 made between a score of 0 and 59. Then 160 made between a score of 60 and 79, and 100 made between a score of 80 and 100. So note that in analyzing tables such as the one above, it is usually helpful to sum the rows and columns, and so that's what they've included for us here in this case. But if you're only given the table, it might be a good idea just on your own to sum all those rows and columns for that. Okay, so if we're given all these questions to find probability based on that information, let's say we were asked, what is the probability that someone in this group uses the guess strategy? Well, if we're saying what's the probability of that, then we would take the total number who used the guess strategy, which was 300, and divide it by the total number in the sample, and that would give us a probability of 0.3. If we're asked what the probability is that someone in the group scores from 60 to 79, again, we would take the total that scored 60 to 79, 530, and divide it by 1,000, and that's going to give us a probability of 0.53. If we're asked what the probability that someone in this group does not score 60 to 79, all we would need to do is take the complement of that, and by doing that we would just take 1 minus whatever the probability that they did score 60 to 79, which is 1 minus 0.53, and that gives us a probability of 0.47. Then if we're asked what is the probability that someone in this group chooses strategy answer C and scores 80 to 100. And so how we would do that is we're essentially just looking for the probability that they chose C and they scored 80 to 100, which is just going to be this 115 number. And so we would take 115 divided by 1,000, and that would give us a probability of 0.115 in this case. If we're asked what the probability that someone in this group chooses strategy longest answer, or, so this was the probability of choosing answer C and getting a score of 80 to 100. What's the probability that someone will choose the longest answer, or they will get a score from 0 to 59 in this case? So for this, what we have to do is we have to take the total who guessed the longest answer and the total who scored between 0 and 59. So the total, the total who chose the longest answer, which is 380, and the total who scored from 0 to 59. But from there, we have to eliminate those that chose the longest answer and scored 0 to 59 in this case. So essentially what we're looking at is if these are independent, then we have the probability of A or B is essentially equal to the probability of A plus the probability of B minus the probability of A and B in this case. So that's essentially what we're looking at, and then divide that by the total number that's in the trial right there. So we're taking the probability that they chose the longest answer plus the probability that they scored from 0 to 59 minus the probability that both of those events happened, which would be 45. So that would give us a total of 0.455 as our probability for that one. Then if we're asked what is the probability that someone in this group chooses a strategy guess given that his score was 0 to 59. So right off the bat, we kind of have three different sets right here. We have one that's asking for the probability of two scenarios when it's and, one where it's or, and then one where it's given right here. And so if it's given, essentially what we're going to do is we're going to take the probability of guess given that their score was 0 to 59. And so what we have to do essentially, or the formula for this, is if we're given the probability of A given B right here, what that's going to equal is the probability of A and B divided by the probability of just B itself. And so if that's the case, A and B, that would be guess and they scored 0 to 59. So we would come here, we would find our guess and they scored 0 to 59. That's going to be 40 right there. And then just the probability that their scores were 0 to 59 is going to be the total, so 120. So it's going to be 40 divided by 120, which gives us a probability of 0.333. Then if we're asked what is the probability that someone in this group scored 80 to 100 given that they chose the strategy longest answer. And so again, we're looking at the probability of A given B. So the probability that they scored 80 to 100 and they chose the longest answer, which is going to be 135 right here, divided by the probability that they just chose the longest answer, which is 380. So 135 divided by 380, which gives us a probability of 0.355 in this case. Okay. Then we're asked, are the strategy guess and scoring 0 to 59 independent events? And so really we're looking at rules now based on independent and mutually exclusive events. And so another way of thinking this is that, is the test taker using the guess strategy unaffected by scoring 0 to 59? And really the answer is no, okay? Because how you could mathematically test independent events is you would say if the probability of A given B is equal to the probability of A. if it's equal to the probability of A. So if in this case the probability of A given B, given that they scored 0 to 59, if that probability is the exact same as the probability of them just guessing, then those two events could be considered independent. But because 0.33 is not the same as 0.3, the two events are not independent. Because they don't equal one another, they're not considered independent. So that is knowing that they were using the guess strategy tells us something about their score in general. Okay. Then if we want to find out whether something's mutually exclusive, we could ask, are the strategy longest answer and scoring 80 to 100 mutually exclusive in this case? That is, are these events disjoint and cannot occur simultaneously? So since the probability that P is the longest answer and scoring 80 to 100 is not 0, then the two events cannot be mutually exclusive. So in other words, this right here, the probability of A and B has to equal 0 in order for the events to be mutually exclusive. If that's the case, so if they are mutually exclusive, then we can use this formula right here for the probability of A or B. Notice that when we were trying to find the probability of A or B for this example right here, because those aren't mutually exclusive events, what we have to do is we have to take the probability of A plus the probability of B minus the probability of A and B, because they're not mutually exclusive. So we have kind of two different formulas that we can use for the probability of A or B. It's either this if they are mutually exclusive, or this if they are not mutually exclusive. So one or the other, basically, for that. So mutually exclusive really only pertains when we're looking at the probability of A or B in this case. Let's look at another example right here. So on university campus, 60%, 30%, and 10% of the computers use Windows, Apple, and Linux operating systems, respectively. A new virus affects 3% of the Windows, 2% of the Apple, and 1% of the Linux operating systems. What is the probability a computer on this campus has a virus? And so, again, we're kind of given this plot right here to show us that there's 60% Windows operating systems on campus, 30% Apple, 10% Linux. Sorry, kind of blanked there for a second. There's a 3% chance that the Windows operating system is going to get a virus, a 2% chance that the Apple operating system is going to get a virus, and a 1% chance that the Linux operating system is going to get a virus. So if we're asked to find the probability that we will just get a virus on this particular campus right here, what we have to do is we have to take the probability of each one of those scenarios happening. So the probability that it is a Windows operating system and it gets a virus, which would mean that we would take the probability that it's a Windows operating system times the probability that it gets a virus, which is 0.03. That should say 0.03. Sorry about that. And that gives us a probability of 0.018. And we would do the same thing for the Apple operating system and the Linux operating system, which would give us both a probability of 0.006 and a probability of 0.001. And then from there, if we want to find the probability that any of those computers has a virus, then we would just take all three of those probabilities, or the separate probabilities, and add them together, which would mean 0.018 plus 0.006 plus 0.001 gives us a total probability that any computer on campus having a virus of 0.025 in this case. Now, let's say we can take the above analysis, or the one right before, one stage further and answer such questions as, if a randomly chosen computer on this campus has the virus, so given that it has a virus, given that a computer has the virus, what is the probability that it is a Windows machine in this case? So again, we're trying to find the probability of A given B. Okay, that's always going to equal the probability of A and B divided by just the probability of B. Okay, so given that it has a virus, so that's the probability of B in this case. So we're always going to divide by the number that we just found, 0.025 in this case. We want to find, but we also want to take all the probabilities that we found when we took Windows and a virus, or Apple and a virus, so on and so forth. So When it is a Windows machine, we would have a probability of 0.72. When it's an Apple machine, a probability of 0.24. And when it's a Linux machine, a probability of 0.04 in this case. So hopefully that makes a little sense as far as some of these formulas for probability goes. Now let's look at binomial distributions. And so these are going to be different than just kind of you basically finding probability in the way that we've just found it in all these examples before. So a binomial distribution is a distribution that can be that meets the following four conditions, or the following four conditions are true in order for this to be considered a binomial distribution. So there must only be two outcomes. One is considered a success and the other is a failure. The outcomes are independent of one another, so we have to pass this test for independence right here. So the probability of A given B has to equal the probability of A in order for it to be a binomial distribution. There is a set probability for success, and there is a set number of trials in this case. And so you can think of this as tips. There has to be two outcomes. They have to be independent of one another. There has to be a set probability, and there has to be a set number of trials in this case. And so this is the formula in order to find that, which is kind of lengthy. There are two other ways you could find this, depending on the question that you're given. You can go to, let me make sure I check this right. Yes, you can go to second vars, and you can use two functions for this, either binom PDF, so binom PDF, or binom CDF. Okay, they're both A and B. You would just have to hit the up arrow key, and you can find both of those functions down towards the bottom of the calculator. But both of those are going to be fairly useful when you're looking at problems of a binomial distribution sort. So suppose that the probability that a light bulb is defective is 0.1. So the probability of being a good light bulb is 0.9. If we're asked these questions, what is the probability that 4 light bulbs in a row are defective? What we could do is we could just take the probability that they're all 4 defective, so 0.1 times 0.1 times 0.1 times 0.1, or 0.1 to the 4th power, and that would give us a probability of 0.001. On the flip side of that, we could also, let me make sure that this actually works correctly. Yep. So on the flip side of that, you could also take second vars, go to binomial PDF, or binom PDF, and then your trials would be 4, your probability would be 0.1, and your x value would be 4 as well, because we're trying to see if all 4 out of the 4 trials are defective. In all honesty, I mean, whichever way kind of makes most sense to you is completely fine to solve this problem. In some instances, it may be easier for your brain to kind of understand that, okay, I've got 4 instances of a light bulb being defective, and so I know that I'm going to run the probability of it being defective 4 different times, so I'm just going to take 0.1 times 0.1 times 0.1 times 0.1, and that's going to give me my probability at the end. Either way, it should work for you. Okay, then we could check what is the probability that only 2 of the 3 light bulbs are defective, and so in that instance we could take the probability that the first light bulb is bad times the probability that it's good times the probability that it's good, and that gives us a probability of 0.009, and we could do that for each one of the scenarios, basically, where the second one would be bad or the third one would be bad. And then what we could do is we could take all of those probabilities, add them up together for all 3 of the scenarios, and that would give us a probability of 0.027. Again, you could also use binomial PDF, and we could stick in, for the trials, this one would be, there are 3 trials with a probability of 0.1, didn't mean to do that, and an x value of 2 in this instance. And so let me make sure that that works correctly. So we have 3 trials, 0.1, 2. And yep, you would get the exact same answer for this. So either way works. In this instance, I tend to think that the binomial PDF would work a little better. But notice how we're using binomial PDF when we absolutely know that what is the probability that only 2 of the 3 are defective? What is the probability that 4, like significantly, like 4 values or 4 light bulbs? When we know that significant value right there, that's when we use binomial PDF. In this case, we would do the same thing. What is the probability that exactly 3 of the 8 light bulbs are defective? So in this case, we would use binomial PDF, and our trials would be 8 in this case. Our probability would be 0.1, and our x value would be 3 in this case. And so from that, we could find the probability that 3 of the 8 are going to be bad, which is 0.0331 in this case. So you use binomial PDF when you know exactly how many successes, in this case, you actually have out of the total number of trials. Okay? For this one, Joe DiMaggio had a career batting average of .325. What is the probability that he would get at least 1 hit in 5 official times at bat? So we could sum the probabilities of exactly 1 hit, 2 hits, 3 hits, 4 hits, and 5 hits. However, the complement of at least 1 hit is 0 hits in this case. So what's the probability of getting no hits in this case? Now, there's a couple ways that you could do this. You could use binomial CDF if you were trying to find at least 1 hit in this case. However, the way that they solve it, by taking the complement of that, the complement of getting not at least 1 hit, is getting no hits at all. That's the opposite of that. And so from there, at that point in time, we would also use binomial CDF as well, or PDF, excuse me, binom PDF as well. And our trials would be 5. Our probability of not getting a hit in this case would be 0.325, or our probability of getting a hit, would be 0.025, and our x value would be 0 in this case. And so that would give us a total probability right here of 0.140. If I want to find the complement of that, though, I have to take 1 minus that probability right there to give me my actual probability that he will get at least 1 hit in this case. So it's still probably more appropriate to use binomial PDF because we are checking to see the probability that he gets 0 hits in 5 total trials. However, we would have to do a little more math, like we would have to figure out the probability that he does not get a hit in certain instances in order to use binomial CDF. But if you can use binomial PDF in most instances, that's where I would go for this. Now here's another example of using binomial CDF in this case. So a grocery store manager notes that 35% of customers who buy a particular product make use of a store coupon to receive a discount. If 7 people purchase the product, what is the probability that fewer than 4 will use a coupon? Okay, so in this case, the fewer than 4, that's kind of the word that I'm trying to get at here, is we don't know specifically if we were asking for the probability that exactly 4 will use a coupon, then that's a point in time when we would use binomial PDF. However, when we're looking for fewer than 4, so when x is less than or equal to 4, or just less than 4, that's when we can use binomial CDF. Now, one thing that I kind of noticed whenever I was grading the AP mock exams is that if you are going to use this function to solve this, number one, make sure if it were fewer than or equal to 4, you would have to include a 4 right here and not a 3. But because they just say fewer than 4, you have to make sure that you don't include that 4 as a successful trial in this case. The second thing that you need to note is if you are going to use any function, binomial PDF, binomial CDF, whatever, you have to list what these numbers represent inside the parentheses. So you can't just write this out and get credit for it. In fact, this would get you no credit at all. Even though you put the right function and you have the right answer, you didn't necessarily specify what each one of these numbers represented in this case. And so if you are going to use binomial CDF, I would write out trials is equal to 7 in this case. The probability, or P, is equal to 0.35, and you could put X. I think you could put successes or X or something along those lines. I'm just going to put X is equal to 3. But you have to make sure that you state what each one of those numbers are in order to get full credit for that particular problem. But hopefully that makes a little more sense as to when you use binomial PDF versus when you use binomial CDF in this case. Okay, let's move on to geometric probability. So that's binomial probability. Geometric probability is fairly similar, but there's one distinct difference. So this is a distribution can be considered geometric if the 4 following conditions are true. There are only 2 outcomes, which is like binomial. One is considered a success, one is considered a failure. The outcomes are independent of one another. There is a set probability for success, so all 3 of those are the same, but the difference is that trials continue until a success is achieved. So there are unlimited trials, essentially, for this. And when you look at the functions in the calculator, you'll note that that's essentially what it is. They don't give you a set number of trials in this case. And so this is the formula for geometric, and this honestly is not terrible. This is the probability for failure times however many times you actually failed times the probability for success, or to the power of the times that you failed times the probability for success. You can also, once again, go to second vars, and you can use either geometric PDF, so geometric PDF, or geometric CDF in this case. So let's look at an example of how we might do that. So suppose only 12% of the men in ancient Greece were honest. What is the probability that the first honest man, Diogenes, however you say that word, encounters will be the third man he meets? And so in this case, it's fairly similar. Will be the third man he meets is definitive. That's actually when he gets to the third man, this is what happens. So in this case, we would use PDF. And so the probability would be 0.12, and our X value would be 3 in this case. And that should give us the probability that we need. So again, we could go to second vars, use geometric PDF, and again, our probability would be 0.12, and our X value would be 3 in this case, because that's the third man that he meets, and that's going to give us the exact same probability of 0.0930 in this case. So that's a function that you can use for that. Then if we're asked what is the probability that the first honest man he encounters will be no later than the fourth man he meets. Again, not a definitive value, but no later than the fourth man that he meets. And so in this case, let me make sure that this works. 2. Yep, perfect. Okay, so for this one, we would again go to second vars, but we would use geometric CDF, not PDF in this case. And again, our probability stays the same at 0.12, whereas our X value now changes to 4 because it's no later than 4. And so at that case, that would give us the exact same probability of 0.4003 in this case. So hopefully that distinguishes when to use geometric PDF and when to use geometric CDF when we're describing both of those geometric distributions. Now let's look at discrete random variables. So discrete random variables are basically when the outcome of an experiment is a real number, i.e. how many heads in 10 flips of a coin. Our expected value in this is the probable number of successes in a set number of trials. And the formulas for our expected values for mean and standard deviation look something like this, something kind of awful and terrible. Now, when we're looking at an example to find the discrete random values, a highway engineer knows that his crew can lay 5 miles of highway on a clear day, 2 miles on a rainy day, and only 1 mile on a snowy day. Suppose the probabilities are as follows. So we have an outcome where it's clear, rain, or snow, and our probability that they can lay 5 miles of highway on a clear day is 60%. The probability that they can lay 2 miles on a rainy day is 30%, or the probability that they can lay 1 mile on a snowy day is 0.1, so, or 10%. So what are the mean or expected value and the variance when we're looking at this? So again, all we would need to do is take 5 times the probability that they lay on a clear day, plus 2 times the probability that they lay on a rainy day, plus 1 times the probability that they lay on a snowy day, and that gives us our mean probability of 3.7, or our mean variable, our mean variable, not probability, but mean variable of 3.7, whereas the variance would be taking that 5 miles minus the mean mile of highway that they can lay total, which is 3.7, square that times the probability that they lay on a clear day, the number of miles that they lay on a rainy day minus the mean number of miles that they lay squared times the probability that they lay on a rainy day, plus the probability that they lay, or the number of miles that they lay on a snowy day minus the probability, or minus the mean miles squared times the probability that they lay on a snowy day, and that gives us a total variance of 2.61. So that's how we would solve either one of those problems in this case. We can also use some of this to solve for our discrete random variables as well. And so when we look at this example right here, these formulas right here for mean and standard deviation are mostly what you're going to be asked to find. There are some instances of variance like that example that we just saw, so you would use either one of those as well, but mean and standard deviation are probably what you're going to see more of. And so in this example, 60% of all buyers of new cars choose automatic transmissions. For a group of 5 buyers of new cars, calculate the mean and standard deviation for the number of buyers choosing automatic transmissions. So again, we know that there's a 60% chance that all buyers of new cars are going to choose automatic. If we're given 5 buyers of new cars, how can we calculate the mean and standard deviation for the total, or for the number of buyers choosing automatic? If we have 5 buyers and they have a 60% chance, that means that we're going to have 3 buyers, or a mean value of 3 buyers out of those 5 that probably choose an automatic transmission. If we're asked to find the standard deviation of that, that's going to be the number of buyers total, which is 5, times the probability for success times the probability for failure. Take the square root of that value. And so 5 times the probability of success of 0.6 times the probability of failure times 0.4. Take the square root of that. That gives us a standard deviation of 1.1. So just to summarize all of it, we have the law of large numbers, which states that in the long run, a cumulative relative frequency tends closer and closer to what is called the probability of an event. The probability of the complement of an event is equal to 1 minus the probability of the event actually happening. 2 events are mutually exclusive if they cannot occur simultaneously. If 2 events are mutually exclusive, the probability that at least one will occur is the sum of their respective probabilities. More generally, the probability of A or B, if they're not mutually exclusive, is the probability of A plus the probability of B minus the probability of A and B. The conditional probability of A given B is given by this formula of the probability of A and B divided by the probability of B. And then if two events, A and B, are independent, then the probability of A given B must equal the probability of A. That is, the probability of one event occurring does not influence whether or not the others occur. Then, if we're given 2 events, A and B, if they are independent, Then the probability of A and B is the probability of A times the probability of B in this case. Then a random variable takes various numeric values, each with a given probability. The mean and expected value of a random variable is calculated by epsilon of x times the probability of success. So however many trials you have times the probability of success, while the variance is epsilon of whatever value we're on. So adding all of those up together minus whatever mean we found right here squared times the probability of success in that particular instance right there. And then for binomial, the binomial distribution arises when there are two possible outcomes, the probability of success is constant, and the trials are independent. And in a binomial distribution, the mean number of successes, or N of P, and the standard deviation is N of P, or the number of trials times the probability for success times the probability for failure. Take the square root of that, and that gives you your standard deviation in that case.